Good morning, everyone. Is the mic working fine? Okay, thank you. Good morning, everyone. My name is Nicolas Lutz. I'm a postdoc at the University of Sherbrooke in Canada, and soon to be a professor assistant at the University of Montpellier. And I'm presenting to you today our paper called Fast Orientable Aperiodic Ocean Synthesis using tiling and blending. Oh, okay. Deep ocean generation and rendering is important for the plausibility of a real-time virtual world containing large bodies of water. It's not as simple as taking a plain mesh and coloring it blue, though, because it requires simulating the movement of the waves and the behavior of light on the surface. The ocean spectrum is an object that represents the ocean in the frequency domain. Ocean wave spectra have been measured from real oceans using oceanographic measurements, giving us analytical expressions of the spectrum. In theory, this allows to simulate ocean waves from an inverse Fourier transform. In practice, though, an inverse Fourier transform with a large spectrum is too expensive to compute an entire ocean. Ocean generation is instead typically carried using the Tessendorf model, which consists in computing a small periodic displacement map, which is used to displace the waves, and normal map used to shade the surface, generated by an inverse fast Fourier transform of an ocean spectrum and a tide-dependent phase. So in this figure, this is an illustration of the approach. An inverse fast Fourier transform computes a small displacement map that is periodic, and then we can repeat this displacement map on the entire surface to get an infinite displacement. The resulting periodic ocean exhibits tiling artifacts, which come in the form of aligned repetitions. This is an issue for immersion, because when modeling an ocean, one does not expect it to tile on the surface. Here is a visualization of the corresponding displacement map. In the past, we have noted two different ways of hiding periodicity. The first is to mix the periodic displacement map with Perlin noise or other noises, which shifts periodic values to periodic statistics. The other one is to overlap several sub-displacement maps overlapped at different tiling scales, like in the figure on the right, which requires to compute several sub-inverse fast Fourier transforms, but significantly increases the actual period of the ocean. In our experiments, mixing a periodic displacement map with Perlin noise is either too periodic when the weight of the noise is low, or looks too much like noise when the weight is high. On the other hand, the periodicity of individual sub-displacements is still visible, especially for low-frequency waves, which tend to be the tallest. So neither solution is satisfactory. In the field of procedural texturing, the issue with periodic tiling is well known, and real-time by-example texture synthesis is a tool that is used to solve the issue. It consists in generating textures directly in the fragment shader using an exemplar as model, for which we try to reproduce the statistics or the appearance without repetitions. Tiling and blending, in particular, is a popular algorithm which consists in blending the content of 3 hexagonal tilings on the surface, like so, on a regular grid. And each of the content of each hexagon is sampled randomly in the exemplar. Our solution to get an aperiodic ocean is therefore to compute tiling and blending using as exemplar both the displacement map in the vertex shader and the normal map in the fragment shader, both being given by the Tessendorf model that is computed in the compute shader. This approach is illustrated in this figure with a displacement map that is obtained with a Phillips spectrum. By definition of tiling and blending, the resulting ocean is fully aperiodic, meaning that it does not tile whatsoever, as can be seen with the displacement map. Tiling and blending allows us to introduce another enhancement, which is to control the orientation of the waves without stretching or distortion. The orientation is fully arbitrary and is given by a flow map for additional offering control, as you can see here on the left of the video. If you're curious about how this works, it works by rotating individual tiles. We first sample the flow map at the center of a hexagon, which gives us an orientation of the waves, and we use the orientation of the waves and the direction of the wind to deduce a single angle per tile. With that angle, we then rotate the indices that are normally used to sample the displacement map or the normal map around the origin by that angle, like if you were rotating a hexagonal piece of texture. We then rotate the displacement or normal vector that is sampled around the up vector, kind of like if you were correcting a normal after a rotation of a normal map. Finally, to smoothly transition from one angle to another, we only have to rely on the blending that is inherent to tiling and blending. In our paper, we propose another enhancements with regard to lean mapping. So lean mapping is a filtering technique that allows to filter specular lobes when the surface is shaded with the Blindfunk shading model. In this figure, you can see that the correct filtering in the middle is somewhat less bright and less noisy than a simple normal mapping on the left, and that lean mapping on the right is much closer to a correct filtering. This requires an additional texture set that I'm going to call in this presentation the lean map, which represents the mean and second order moment of the normals under each MIP map footprint. So this is a little more expensive to compute, but it allows for a more realistic ocean or a surface with a normal mapping. In 2022, Charline Grenier showed that it was compatible with tiling and blending, meaning that it is inherently compatible with our ocean. Things are a little more complicated when we want to use lean mapping with a flow map, though. And in our paper, we show that theoretically, lean mapping with a flow map will require one lean map per angle, which will therefore require an infinite amount of lean map. We also show, however, in our paper, that we can express the components of each of these lean map as a linear combination of the components of the original unrotated lean map, which is a new and interesting result, possibly not only for ocean rendering. What's to take from this figure is that if you do not correct the lean map, your specular lobe is going to look way off on the right. To assess the quality of our ocean, we use the tool known as the autocorrelation function, which represents the second order moment, or rather the centered normalized second order moment of a stochastic process. If you don't know exactly what this means, the autocorrelation function can actually be expressed as the inverse Fourier transform of the power spectrum, and therefore an ocean spectrum. When we compute the autocorrelation function of a real ocean, we notice that it rapidly converges towards zero when increasing the distance, following this shape. When we compute the autocorrelation function of several ways to compute an ocean, we notice that ours is the only one that has such a shape where the autocorrelation function rapidly converges towards zero as the distance increases. This shows not only aperiodicity, by definition of the autocorrelation function, but also a better fit with a real ocean on the second order moment. If you're curious about how this is computed, you can check out this previous article of mine. The size of the synthesis tile, interestingly, has a direct impact on the autocorrelation function, where having large tiles slows the rate at which the autocorrelation function reaches zero. Other than that, in terms of look, having tiles that are too small introduces high frequency waves due to rapid shifts from the content of one hexagon to the next. whereas having tiles that are too large reintroduce local periodicities due to each hexagonal tile encompassing several periods. In terms of computation times, there are a few interesting things to note. First, we did not change the generation of the initial tile, meaning that the computation time are the same. The rendering is a little slower because the displacement map and the normal map respectively both require the final displacement map both require to sample 3 times the initial displacement and normal map respectively. It is much faster than multiple sub-displacements, although we do note that in theory, when using multiple sub-displacements, you could just cut the frequencies that are not used for the sub-inverse fast Fourier transforms. The flow map in our experiments costs about 0.1 milliseconds more when in use, so it's really cheap. Lean mapping is quite more expensive because it requires about 1.4 milliseconds when not optimized. Our application is not exactly optimized, and one of the possible optimization which is pretty important, would be to encompass the normal map inside the lean map, which would cut the computation time of lean mapping by about half. What's to take from all of this is that our ocean is very little more expensive to compute, but it's the only one that allows for a true aperiodic ocean and with a better second order moment like I showed you earlier. Now there is an interesting limit to note regarding variety, which is linked to tiling and blending itself. In tiling and blending, variety is only as high as the exemplar, so in this case as the original tile, which leads to repetition. So in this figure you can see that I have circled several displacements which kind of look a little bit the same. Now in practice, repetitions are hard to see for 3 reasons. The first one is that the displacements are actually blended with other displacements from the original displacement map, which means that, as you can see, they're not always exactly the same. The second reason is that you're not actually visualizing a displacement or normal map. You're rendering an ocean surface, which can be boiled down as a bluish mesh with a displacement. So repetitions are harder to see. And finally, if you were to try to spot a repetition, it will be hard to do because the animation makes it so that by the time you look from one place to another, the repetition is already gone. So interestingly, for this application, tiling and blending has less visible repetitions than, say, for synthesizing a static texture. There is another interesting discussion to have about artistic control, which is related to the fact that when using multiple sub-oceans, you have an additional offering control due to the fact that you can control the individual sub-displacement map individually and normal map. For instance, you can increase the weight of the low-frequency waves or the height, which to my knowledge is something that is done in Sea of Thieves. Ultimately, our synthesis is compatible with any periodic map, which means that it is compatible with, which means that we can use it on any or all sub-oceans. For instance, you could decide to only synthesize the low-frequency waves and keep the authoring control that multiple sub-oceans allows you to have. In conclusion, we have presented 3 main contributions: a new fast and efficient way to periodically tile an ocean using an existing algorithm in texture synthesis, a way to control the orientation of the waves with a flow map without stretching or distortion, and we showed how to execute a lean mapping when using a flow map. In the future, we would like to hasten the generation of the initial displacement and normal maps, for instance using noises that are well known in texture synthesis or procedural texturing, such as Gabor noise. We would also like to provide more control, for instance by controlling wave amplitudes using different wave spectra or especially varying wave spectrum when according, for instance, to the distance with the coast or special weather conditions. Thank you for listening to my presentation.
Excellent. Do we have any questions?
Did you consider just taking all this and replacing all of that with AI?
Well, sure, why not? But the issue with AI right now is that it's simply not as fast as just having a good analytical expression and just evaluating it. So tiling and blending right now, it's still faster than any AI model. And since I'm not an expert in AI, I'm not going to look for a process that is faster than that.
Any other questions? I had one when I saw the flow model or the flow field part of your contributions. I thought, hey, this might be interesting. What do you think the limitations would be if you had a flow map that came from, let's say, an atmospheric model to try to give some physically based, like physics simulation plausibility to this? Like, what kind of issues or limitations do you think there would be with that?
Can you repeat the part with the physically based?
Yeah. So I mean, I come from scientific computing background, so I deal with atmospheric models where they're computing wind. And of course, once you have wind, you could have a flow field. With a flow field, you could be visualizing how the ocean might look under such wind conditions. Do you think there's like interesting possibilities there or issues that come to mind? I know this is on the spot, but what would you think?
Well, what I'm thinking right now is that the flow map that we propose does not actually look very realistic. You can see that the ocean is doing some kind of S right now. It's more for spatial offering control, for instance, if you want to have a cool ocean like this that just goes to the center. For instance, if you have let's say a singularity in the world, who knows? Right now, I don't know exactly what you could do with a more physically based model. I think it would be interesting to try. We haven't gotten very far with the flow map. One thing that we didn't even try to do, for instance, yet, is to have a flow map that you can change in real time. That would be interesting to do, and that would also correspond to reality more.
Very good. Any other questions? Over here?
Yeah, so assuming you have a very large velocity in the flow map, I think we need to suffer some.
Can you speak up? Sorry.
Yeah, so I'm saying if you have very large velocity from the flow map, I think we need to suffer in some stretching artifact flow method.
I'm not sure what.
I think to understand your question, if you had large velocities in the flow map, what kind of artifacts that would generate?
Like stretching artifact or other distortion.
Right now, in this application, the velocity of the waves is fixed. It's determined by a user-defined parameter. So when the flow map that we propose is only a bunch of directions. They're not they don't actually have a velocity tied to them, and I'm not sure how that would work, because the issue is that the animation is entirely carried in the Tessendorf model. So we're just taking the Tessendorf model and synthesizing it. So in theory, you would have to do something else, like having several animated oceans and blending them, for instance. So right now, this what you propose isn't quite possible.
All right. Quick question.
Another quick question. How about the wind in the ocean? Do you consider if you have a lot of wind over the waves, and that would change the appearances somehow?
Right now, when using the flow map, the wind doesn't come into place. It's not it's irrelevant, and it's irrelevant. So right now the wind can't influence on the ocean when you control it with a flow map. What you would need to do is probably compute two oceans and blend an ocean that is subjected to wind with an ocean that is subjected to a flow map. That's at least how I would do it, and maybe control the weight with maybe a spatially varying map. That would be possible. But right now with this application with a single ocean, it's either use a flow map or use the wind condition, or use the wind. Although you could obviously continue to explore this direction.
Okay, I think we're out of time. Let's thank our speaker.